Here we are at the College Board website for the AB Calculus course, the BC Calculus course. Of course, a course would look very similar to this. We're here because we're going to unpack a particular free response question having to do with implicit differentiation. I want to give you a sneak preview of what this thing looks like. So I'm going to click the exam tab, and it's not going to hurt to go over this one more time, the format of the exam. You've got two parts, multiple choice, and the second part free response. Multiple choice is broken up into two sections, the first one without a calculator, and the second one with a calculator. Free response questions, you've got 6 of them, and the first 2 is with a calculator, and then the last 4 without a calculator. 3 of these are common on both of the AB and BC calculus exams. You have the exact same questions. The other 3, though, wild cards. All right, so I'm going to scroll down here to the free response section and actually look at some past exam questions. Am I? I think it's loading. Please be patient. Okay. All right, and in particular, I'm going to go down to, here we go, 2015, and let's go ahead and take a look at these questions. All right, I already have this in Notability, so you can see that these were the 6 released questions on the AB Calculus exam. And again, 3 of these questions would have been exactly the same on the BC exam. Question number 6, however, is not, because question number 6 on the BC exam is ordinarily your series question. Okay, so let's take a look at this thing. Consider the curve given by the equation y cubed minus xy is equal to 2. It can be shown that dy dx is equal to y over 3y squared minus x. All right, a couple of things. First of all, let's take a look at this equation. That equation right there is not one that, let's say, for example, in a pre-calc class you would ever have had to graph or probably even to solve, because you've got multiple y's in here, and this one's to the 3rd power. What the heck? Okay, and then when we look at our derivative, at this point, when we found the derivative of a function, it was always a function of x. And notice that this is both a function of x's and of y's. That's pretty crazy. Okay. So this is what we're going to learn how to do in this particular lesson. Let's look at the 3 parts of this free response question. Write an equation for the line tangent to the curve at the point -1, 1. Well, how easy is this? Because you only need 2 pieces of information, the point, which they give you, and a slope. How do I find the slope? I plug this point, x comma y, into the derivative, and I can very easily get the slope. And I can put those things together to write the equation of the tangent line. Because remember that the derivative as a function, or a function of x and y in this case, it gives us the slopes of the tangent lines. And prior to this point, again, we would have only had to stick in the x value, but here you can see that we have to stick in both the x and the y value. Part B, find the coordinates of all points on the curve at which the line tangent to the curve at that point is vertical. Vertical. Vertical means that the slope is undefined, that the slope is going to either positive or negative infinity, and that's going to happen when we take a look at this derivative here, when the bottom is equal to 0. Again, something that would be pretty easy to do. And then finally, part C, evaluate d2y over dx2 at the point on the curve where x is equal to -1 and y is equal to +1. What does this mean? Does this mean that we're supposed to square the derivative? No, it means that we're supposed to take the second derivative. And again, both finding the first derivative and finding the second derivative involves what this lesson is all about, which is called implicit differentiation.